we were trying to find the torque on this sort of pulley system, right, where we had the two weights with the ball. And question D said use two different methods to read it anymore to find the net torque on the pulley. And what I told you was that you could calculate it either by using I alpha or calculating these two torques and adding them together. Like the answer was on there. Did you guys figure that out? Do you need me to go over it? Where are we at? Nice. Is everybody okay with it then? Yeah. Going once. Going two times. So very good. Okay, so if you do that, the net torque ends up being, and it actually, like I said in class, should be negative 0.026 newton meters, right? Okay, so finally E and F. So these are new equations to this section. So E and F ask you for the average power and the instantaneous power. So probably worth taking a second and jumping back. So here are the two equations we learned. To calculate the instantaneous power, previously we just did force times velocity. And now that we're talking about rotational, it's torque times omega. All right. Now it turns out that even if something is rotating, you can still do force times velocity. If you do the force producing the torque times the velocity of the object at that point, it gives you the same result that doing torque times omega does. Rationale being that torque is force times radius, and omega is velocity over radius. Right? So if you do torque times omega, your r's cancel. You just get FB. Okay. So, so the last two questions then were to find the average power and the instantaneous power. So, average power, we got to figure out how much work was delivered to the pulley and divide it by the time it took. So, thoughts about how to find those two values? Good. Find the change in energy for the pulley, right? Okay, and then divide that by the time it took, right? Okay, so I think the time is really the biggest obstacle here. So we need to rewind and refresh our memory a little bit about some stuff. So let's see, what do we know? We know that our we know that our final velocity was 1.6, and we know that our linear acceleration is 1.7, right? So I think we can use that information there to find the time. So we got E. So E, our time is, well, that's just VF minus VI over A, right? Just rearranging the acceleration equation. So our final velocity was 1.6 meters a second. Our initial velocity was 0. Our acceleration is 1.7 meters a second squared. So divide that out, you get a time of 0.94 seconds. Okay, so now we just need to find the work. And so there are a couple ways you can do it. You can do what Patrick said, find the change in rotational kinetic energy. You can also, remember, find your work by doing net torque times change in theta. Okay, either one of those works. Follow? Okay, so I ended up doing it just using the change in RKE. So, because I know that my RKE initially is 0, and my RKE final is, well, that's 1/2 times I. Did we find I at some point earlier? Oh yeah, you found it when you did torque equals I alpha, right? So 1/2. So I is, did I write it down somewhere? Yeah, so your I is 0.007. Oops. Yes. Oh, I'm sorry. Yes. Sorry, that's the notation I'm using with my honors students. Sorry, guys. Yeah. RK is rotational kinetic energy. Sorry about that, Mike. All right, so there's our I. And then omega, I don't know my omega yet, right? But I know V is 1.6. So I can just use 1.6 meters a second over my radius. What was the radius of the pulley? We're almost done here, you guys. 0.05. There are certainly other ways you could have done that. That's a way that works. Okay, and so it ends up giving you 0.384 joules. And so now we can find the power just by doing work over time. Cool. Worth experimenting with. Go back and do this. Do net torque times change in theta. You should get the same amount of work. Okay, you really need to make sure you're familiar with both methods here, right? All right, so power then is work over time. I guess I should put the average, right, to be specific. So our work is 0.384 joules. The time is 0.94 seconds. Divide it out, and you get 0.408. What are the units? Watts. Cool. All right, and then last question C says, what's the instantaneous power at the, how's it worded? At the end of the 0.75 meters, so at the end of the problem, what's your instantaneous power? So you can either do force times velocity, I guess it would be net force times velocity, or you can do net torque times omega. So last thing, question F. Power is, how did I do it? I did net torque times omega. So the net torque we already know is 0.026 Newton meters. And then omega is this 1.6 meters a second over 0.05 meters, whatever that is. It gives you 0.83. Again, watts. Cool. All right, big example, but it hits a lot of key ideas. Notice we used the work kinetic energy theorem, right? We looked at work being force times distance or torque times change in theta. We really had a lot of things here. Conservation of energy was here, right? The whole premise behind the start of this problem was that the gravitational potential energy we lost as the system moved turned into kinetic energy in the system, right? So those are all useful problem-solving tools. Are there questions? Okie dokie. So we said this last chunk of homework was going to be due Thursday, yes? All right, so I spent last night and most of the day today kind of looking through some concept-y, choicey problems. David commented before break, and I've been stewing over this, the fact that I haven't done a great job getting you guys concept-y stuff. It's part of it because I just haven't had time or resources. And I totally agree with what you said about Quest. It's a really good way to get a lot of stuff out of it. Just trying to figure out ways to do that here these last few weeks before the AP test. So hopefully I'll be able to come up with something we can do in class tomorrow that'll be constructive. I wish I'd had it ready earlier, but I just haven't had time. Real quick while I'm thinking of it, if you haven't signed up yet to the AP test, the deadline is the 17th of March, so make sure you do that. Yeah. Yes?
Back when I thought last unit was the sheet of them. That's really helpful.
And that's what I'm going to try to do for tomorrow too. So thank you for the feedback on that. Yeah, and I think the test scores reflected that. You know what I mean? Okay. All right. So questions on the second chunk of homework. What do we need to look at? Oh, is there a list up there? Oh, I assume that was the same one as last time. Was it 48, 52, and 57? That brings us
48.
Okey-dokey. Holy cow, what is all this garbage? All right, here we go. 42. Shoot, where did I just had it. All right, so let me see. 42. Oh, right. Okay, yeah, 42 is definitely important, so let's go over that. A real quick comment, unrelated to anything directly. I don't know if you remember last, or the week before break, I showed you guys again how to do a dot product to do force times distance, right? I realize that doesn't actually come up till the next chapter, so I apologize. I showed you that a little bit earlier. That using, say it again?
Mary's.
Yes, thank you. Using Mary's method won't show up until chapter 11. Okay, so. Yeah, remember the, where you do the IJK components.
Yeah.
So I apologize for that. That was my bad. Okay, so let's do number 42. So it says the masses and coordinates of 4 particles are as follows. So the idea is it gives you x and y coordinates of these particles. So let's draw it real quick. I'm not going to be super accurate about it, but let's at least kind of get down. So at a position of 2, we've got this guy, 50 grams. At a position of 0, 4, we've got this guy, which is 25 grams. Formatting on this is terrible. At x equals -3 and y equals -3, we've got another 25. Oh, it's negative 25 grams. What am I doing? Sorry about that. And then 30 grams at -2, 4. Is this right? 30 grams is up here. And then you're trying to find the rotational inertias around each of the axes. Okay? So the first one wants to know the rotational inertia around the x-axis, right? So here's the deal, you guys. Rotational inertia is, for a single particle, the rotational inertia is mr squared. All right? When you're looking at a system of particles like this, you just sum up each of the individual rotational inertias. All right? This is a useful fact, you guys, in the same way that if you're trying to find the total mass of a system, you just add the masses. If you're trying to find the total rotational inertia of a system, you just add the rotational inertias. Okay? Like break it up into little bits and add them up. All right? So we want to add them all up. So for part A, it wants to know, for part A, it wants to know the rotational inertia about the x-axis. So what you want to do is you want to picture this whole thing pivoting around this. So that the 30 and 25 and 50 gram masses are going to be kind of coming this way, right? You guys see that? So your radius of rotation for each of these would be just the y value, right? Follow? So I'm going to do, so what is that? 4 centimeters times, or sorry, 30 grams times 4 centimeters squared plus 4 centimeters times 25 grams. I'm saying it wrong, but you know what I mean. 25 grams times 4 centimeters squared. Same thing here. Same thing here. Notice the negative is going to get squared out, so the negative doesn't affect anything. Okay? And then finally, you can either, I don't know if this is what you're going to ask, let me say this and I'll get your question. You can either give your answer in, usually we do kilogram meters squared. There's no reason why you couldn't do gram centimeters squared and leave it like that. I don't remember what I did on the answer sheet. What did I do? Did I leave it in grams and centimeters? Great. Cool. So, do I need to write that out, or does that make sense? Yeah? Ooh, could you just find the center of mass?
Because the 25.
No, because they have different positions. This one's 4 and this one's -3. So they don't cancel each other out. I will say 2 things to this. My knee-jerk instinct to that is know that it wouldn't work. And B, even if it did, I think they're making it harder than you need to. You know what I mean? Like, I think it's easier to just do it just by finding the 4 inertias and adding them up. Okay? Yeah.
Wait, so how do we know it's moving this way?
Because of the way the question's worded. Question A says, find the rotational inertia of the collection about the x-axis.
Oh.
Cool? Follow? Does anybody want me to write out more for A? I'm happy to if you guys need me to. We good? All right. For B, it wants to know the rotational inertia about the y-axis. So now instead of everything rotating this way, it's going to be rotating this way, right? You guys see what I'm saying? Like out of the board and around this way?
Yeah.
So now my radii, instead of being the vertical y components, are going to be the horizontal x components, right? And this one's going to be 0, right? Does that make sense? Okay, if your radius is 0, your rotational inertia is 0. So this thing has no rotational inertia because it has a radius of 0. Follow? Everybody good? You want me to write it out? All right. And then finally, question C wants to know what's the rotational inertia around the z-axis? Well, the z-axis is going this way, right? So now our r's are going to be, we got to use the Pythagorean theorem. So for this one, here's our r. For this one, here's the r. For this one, here's the r. And for this one, here's the r. Cool? But, super secret ninja shortcut, we don't really need r, we need r squared, right? Oh, why does that help me? Because, so this one, r squared is just going to be 2 squared plus 2 squared equals r squared, right? See what I'm saying? And you're going to square root it and then square it and follow? Is that enough? I always feel like I'm cheating you guys when I don't finish problems. Does that make sense?
That makes sense.
Okay. All right. So that was that. All right. So D. So suppose we symbolize the answers to A and B as A and B respectively. Then what's the answer to C in terms of A and B? Shoot.
And isn't that what you just answered, though? Since the Pythagorean theorem.
Oh, we're right. Yeah. So you're literally just adding. Wait, no, that's not right though. Oh, right. Yes, because yes. So you use the Pythagorean theorem. Right.
Yeah. Wait, since it's squared, it's the step you just went through.
Right. Yes.
Setting it out.
Yes. Oh, correct. Yes. Thank you. Yeah, I was looking at my work. Thank you. Okay. Everybody good with 42? All right, big takeaways from this, you guys, are this idea that when you're looking for the rotational inertia of a system or a collection of objects, you can just add the individual bits. Okay? That's a big concept. Cool? All right, so that was 42. What's next up there? 48? Alex, is that the next one is up there? Thank you, sorry. Should really start wearing my glasses. All right, 48. The length of a bicycle pedal arm is 0.152 meters, and a downward force of 111 newtons is applied to the pedal by the rider. What's the magnitude of the torque about the pedal arm's pivot when the arm is at, and then it gives you different angles with the vertical. Okay, so I kind of pictured this. You've got, here's whatever the little cogs that the chain goes around, right? And then you're going to have a pedal that goes up, and then the other one's going to be down, right? Okay. And then obviously this whole thing, oh, that's not at all what I wanted to happen. outward. Obviously, the whole thing can be rotated at any angle, right? Okay, so let's see. So in the first one, it says, what's the magnitude of the torque about the pedal arm's pivot when the angle is 30 degrees of the horizontal? Okay, so the idea then is, here's my pedal, right? So we're focusing on just one pedal at a time, right? Okay, and it turns out it doesn't matter which one you use for reasons that I'll explain in a second. So the idea is, I know that this D here is 0.152 meters, and your force is always downward, right? Because when you pedal, you're pushing the pedals down. Yes, or yeah, if you have clamps, yes, probably. But the problem says downward force, so you got to interpret it that way. So here's my force. What is it, 111 newtons? 111 newtons. All right, and then you're trying to find the torque. So all you're going to do on this, you guys, is torque is force cross, oh, sorry. It's radius cross force, right? Isn't that the way we wrote it? And this is RF sine theta. So, sorry, I called it D here. But, so this is my R, right? Here's my F. There's 11 newtons. Is that right? What's theta? But like conceptually, what is theta? The angle between the force and the lever arm, technically, and in this case, the pedal is the lever arm. All right? And it tells you that the angle between the pedal and the vertical is 30 degrees. So for A, you're just going to do 0.152 times 111 times the sine of 30 degrees. Cool? And notice, if you picked the pedal in this position, then this angle here ends up being, what would that be, 150 degrees, right? In other words, the supplementary angle, right? And the sine of an angle is equal to the sine of its supplementary angle, right? Because they're going to have the same sort of y position. Good. All right. So either way, you're going to do 0.152 times 111 newtons times the sine of whatever angle is given to you. In the first one, it's 30 degrees. In the next one, it's 90 degrees. Show me with your hands. It says, for part B, it says, what's the magnitude of the torque about the pedal's pivot arm when the arm is at an angle of 90 degrees of the vertical? Show me with your hands which way are the pedals facing there. 90 degrees of the vertical. This way, right? So that's your maximum torque, right? Because now your force is down, so your force is at a right angle to your pedal, right?
Yeah.
Make sense? Cool. All right, and then the last one is 180 degrees from the vertical. So it's the same as 0 degrees, right? So that's when the pedal's vertical and you're pushing down. What's your torque going to be? 0, right? Cool.
If you were just to stand on a pedal, just stand on a pedal, because so like if you think about it, like at this way, at the horizontal one, you have a lot of torque too, because you think have one ability to push down. Right? So like if it was like this, when's the torque you have?
Well, your ability to push down is more or less your weight. I guess technically you can push with a little more force than your weight, but right, if you're lifting yourself. But so the force is fixed. That's just, you know, sort of how strong you are that you can push down, right?
Yeah.
But here it's not producing torque.
Yeah.
Over here it is.
Yeah.
Make sense?
Yeah.
Everybody good? Okay. Is that what you were saying, Marcus? Are you good? Okay. So that's 48. Are there questions on it? Okie dokie. What's next? 52? Am I going too quick, you guys, or are we good? Cool. I'm trying to find the happy medium between spending too long and plowing through stuff too quickly. All right, so 52. Oh, that's right, this crazy drawing. All right, so it says in the figure at the right, a cylinder having a mass of 2 kilograms. So let's write that down. That feels important. The mass of this thing is 2 kilograms. It can rotate about its central axis through point O. Forces are applied as shown. So let me see if I can recreate this stupid drawing here. If I'd been smart, I would have printed it off. All right, so here we go. So F1 is 6 newtons. F2 is 4 newtons. F3 is, where is it, 2 newtons. And F4 is some number that's going to end up not mattering, but I'll write it out anyway, 5 newtons. All right, so there's my drawing, and we know each of these radii. So the big R is 12 centimeters. This one is 12 centimeters. This one is 5 centimeters. And this one is 12 centimeters. Okay, so is everybody okay with sort of what's happening? All right, so all of the forces are being applied at the outside edge of the wheel except for force 3, which is only 5 centimeters from the center, right? So everybody good with the drawing? All right, so what we're trying to do is we're trying to find the angular acceleration of the wheel. So what equation should we be thinking about? What kind of problem is this? It is constant acceleration, I agree with that. Why? How do we know the acceleration is going to be constant?
The force isn't changing.
Because the force isn't changing. Yes, except, so when we talk about force, we're talking about linear motion. This problem isn't about linear motion, it's about torque. So instead of thinking in terms of force equals mass times acceleration, I should be thinking in terms of torque equals I alpha. Followed? So I can find my I pretty easily, right? So let's do that. This is a solid cylinder, right? So I think I is 1/2 mr squared. So that's going to be 1/2 of 2 kilograms times 0.12 meters, right? Because that's the radius of the whole thing. A quick comment on this. When I went through this with my honors students, they got a little bit confused about how you know which R to use. Do you guys all understand why I'm using the 12 centimeters and not the 5 centimeters to find my I?
Yeah.
Everybody? Because it's a property of the object, right? Depending on the size of the object, not where the forces are being applied, right?
Square that.
Okay, yep, and I got a square. So that gives you, what, 0.144? Is that right? Or is it 0.144? Oh, yeah. Kilogram meters squared. Okay, so there's my I. So now to find my alpha, I need to know my what? Net torque, right? So let's find our net torque. So check it out. Let's see. So my net torque. Have to scroll down a little bit. That'll work. All right. So my net torque. Well, that's equal to the torque produced by force 1 plus the torque produced by force 2 plus the torque produced by force 3 plus the torque produced by force 4, right?
Yeah.
So let's see, torque 1 looks to me like it's going to be 0.12 meters, that's my R, times my force, 6 newtons. And is that torque going to be positive or negative? It's from force 1, so positive or negative? Positive. So there are 2 ways you can figure that out. The way that I did it is I just looked at it and I said, well, that's going to make it go counterclockwise, positive. Counterclockwise is positive. Everybody good with that? Or use the right-hand rule. Here's my radius. Here's my force. Thumb points out of the board, so it's positive. Cool? All right. Sorry, that corresponded to the right force. All right, now torque 2, let's see. What's R for my torque 2? Same thing, still 0.12 meters, but now my force is only 4 newtons, right? Positive or negative?
Negative.
Negative, that's going to make it spin clockwise, right? Using the right-hand rule, here's my radius, here's my force, thumb points into the board. So put a negative sign on that torque there. Up. All right. Plus torque 3 is going to be, let's see, my radius is, you can read my crappy writing or look at the drawing. 5 centimeters, right? Times our force, which is just 2 newtons, right? Positive or negative? Is the torque produced by force 3 going to be a positive or negative torque? Negative, right? Because it's going to make the wheel spin clockwise, so that's negative. Or right-hand rule gives you radius, force. Thumb points in. Put in your negative sign. Plus the torque produced by force 4. Oh, it is 0. So I realize now, I wish I kind of glossed over something really important on these 3 torques. What did I neglect to talk about that I should have talked about? The angle. Okay? But if you look at the drawing, and I tried to do the best I could on my drawing, but if you look, there's a little right angle symbol here, a little right angle symbol here, and a little right angle symbol here, which is telling you that in every one of those first 3 forces, the force is perpendicular to the lever arm. Follow? So these are all times the sine of 90, right? Right? In this last one, what's the angle between my radius and my force? 0, right? Okay, and sine of 0 is 0, right? This is that force right there is this. Right? My hand here is force 4 pulling out, right? That's not going to cause the wheel to rotate, right? So this last torque is 0, so add them up. What are you going to get? Let's see. We're going to get 0.24 minus 0.1, so 0.14, is that right? Newton meters for the torque, positive, right? So there's my net torque, and I know my I, so I can find my alpha. Right. Oh, so close to getting it on the board. So alpha is net torque over I, so 0.14 Newton meters over 0.144 kilogram meters squared. That gives you whatever it is, 10 point something or 9 point something. I guess 9 point something, right? What is it? Radians per second squared. What? Oh, like, I think I see what you mean. I'm going to redraw it on a new page. This is a really good question. So that force, if you look at it simply, you've got this. You had 5 centimeters and then a force, right? And you're saying, what if it instead gave you this force and this distance along with this angle? You could just do 12 times the sine of this angle times the force, and that would come out to the same thing. Because when you're doing that, when you use this equation, you guys, when you do FD sine theta, what the sine theta accomplishes is it's either finding the component of the lever arm that's perpendicular to the force, or the component of the force that's perpendicular to the lever arm. Cool? So that's all that sine theta is. And in fact, I used to, when I taught honors in Farmington, I used to teach this. Oh, sorry, I'm writing D instead of R, you guys. I got different notation in here and in my honors classes. I need to get them aligned. Right, that's the same thing. It's saying take the perpendicular component of the force or the perpendicular component of the distance. For lever arm. Cool. Mickey.
The answer on this problem says 9.72 rads per second squared K.
Oh, I'm so glad you pointed that out. Thank you. So why is the K there? Telling, yeah, it's unit vector K. So the idea is our net torque is positive which means our net acceleration is going to be positive, so it points out. I'm really glad you asked that. Thank you. Cool, you guys? All right. Yeah, because it says magnitude and direction, so the K is the direction. All right, look at us go. What's the last number? 57. A pulley. Oh, yeah, okay. All right, so 57. A pulley with a rotational inertia of, oh, what is that? It's got to be 10 to the negative third. Yeah, point. Nope, you're right. I'll make a note. Yeah, I don't know what happened there. Somewhere I have my. I just want to make sure that that's the right number before we solve it. Use the wrong number. No, because it's 1 times. Chapter 10, number 57. Yeah, that 2 isn't even supposed to be there. I don't know what happened there. I must have just bumped the keyboard. Okay, so that's what the I is supposed to be, and if that's what was confusing you, I apologize. That's for sure a typo and a point. All right, so everybody cool? All right, so we know the rotational inertia. We know the radius is 10 centimeters, which I'm going to right away convert to meters. I know that it's acted on by a force applied tangentially at its rim. So let's talk about that, you guys. So here's the pulley. When I say that the force is applied tangentially at its rim, what does that mean? At a 90-degree angle to the radius, right? So if the force is being applied here, here's my radius, here's my force. The force is tangent to the circle. Cool? And if it ever says radially, that means along the radius. Cool?
Yeah.
All right. So that's our little drawing. All right, the force magnitude varies in time. So our force is a function of time. So I'm going to write it as f of t. And it's this, 0.5 t plus 0.3 t squared. With F in newtons and T in seconds. The pulley is initially at rest. At T equals 3 seconds, what are the angular acceleration and the angular speed? So, thoughts about how to do this. Will you guys tell me? Find the torque? Oh, that makes sense. I should be able to. I know that here's my force at time t, and I know it's applied at the outer edge. So my torque as a function of t ought to be that times r, right? Just r times f. And notice this angle is 90 degrees, so I don't even need to worry about my angle. So that's going to give me this times 0.1. So that's 0.05 t plus 0.03 t squared, right? Don't think this is how I solved it, but this will totally work. All right, so there's my torque at a given time. So now what? Plug in the time. I'm going to hold off on plugging in the time, and I'll show you why in a minute. Because eventually we're going to need the angular speed. So what's the connection between angular acceleration, which is being asked for in part A, and angular speed, which is being asked for in part B? Derivative, right? So I want to write my acceleration in terms of t, so I can take a derivative. No, that's totally wrong. We got to integrate. Sorry. Integral. Sorry, integral. We got to take an integral. But regardless, we need to leave it in terms of t so that we can do our calculus, right?
Yeah.
Okay. And I apologize. I misspoke. It's integral, not derivative. Okay, so check it out. I know that alpha is torque over I, right?
Yeah.
So here's my torque, here's my I, right? So this is basically 1/1000th, right? So dividing by 1,000th is the same as multiplying here by 1,000, right?
Yeah.
I'm doing this in my head, so correct me if I'm wrong here, but I think this is what we get. Again, I did it slightly differently, but I think that works. Questions about what I did there? What'd you say? Pretty good. Okay, so question A says to find the angular acceleration after 3 seconds. So just plug in 3 for this. Let's see, does that work? So 9 times 30 is 270 plus 150 gives you 420, so that checks out. Good? Or is the laughing I'm hearing like I have no idea what the hell you're talking about, but I'm gonna, are we good or no? Okay. Oh, I gotcha. Fair enough. All right. Okay. So, okay. So for part B, we got to find our angular velocity, right? So, I'm just trying to think about notation, how I want to write this. So, what's the connection again between acceleration and velocity? We gotta integrate, but when you integrate, so I guess technically what we're doing here is we're taking the integral of acceleration as a function of time with respect to time, but it's a definite integral, right?
Yeah.
We're integrating from time 0 to time 3. But this isn't really right. This doesn't give you omega, it gives you, very good, it gives you change in omega. All right, remember you guys, definite integral gives you the change in the quantity. Okay, this is one of the things we learned this early in the year, but because we've been sort of... All right, everybody good?
Yeah.
All right, now, notice, you guys, we only got a couple minutes here, but we're almost done. What's our starting angular velocity? Yeah, it says starting at rest. So you start at 0, right? So if your change is 500, and you start at 0, then your final is going to be 500, right? Does that make sense? Did somebody say no? Good. Okay. All right. So let's do our what's me together? I go. So the integral from 0 to 3 of alpha. So 50t plus 30t squared with respect to t. So integral of 50t should be 25t squared, right? Plus 10t cubed, and then I want to evaluate between 0 and 3. So if you evaluate it at 0, you get 0, and evaluate it at 3, and you get 500. There's your answer. Make sense, you guys? Yeah. Okay. Those were good problems. I feel like we hit some really good ones today. I feel like I've gotten a little better about trying to be selective about the problems I pick. These all seem like fair game. You know what I mean? Like,
Even the one we did yesterday.
take a look at the homework that goes along with the one we did yesterday. That's the one that's due Thursday.
Yeah.
I think that's probably a better representation. The one we did yesterday would be like an FRQ, and it would be broken up into steps just like that. Probably 4 steps, to be honest. All right, are we good, you guys?
Yeah.
All right, so tomorrow I'm going to try to come in with some kind of concept-y stuff. We'll probably do some concept-y multiple choice stuff kind of in class as a group, and I'll give you more to work on too, okay?
Right.